Welcome to the Fundamental Theorem of Calculus Day 2. To begin our lesson, there is a review on the first page of your note package, so please go ahead and try to do those 3 questions. You're going to take the derivative for the first question. The second question, you're going to take some basic integrals. And then the third one, we're going to look at critical points and finding relative max and mins. So go ahead and try 1, 2, and 3, and then when you're ready, we can go through the solution. All right, so for the first question, we just want to take the derivative. We're using the chain rule here. So the derivative of sine is cos, and then you leave the x cubed alone. Then you'll take the derivative of the x cubed, which is 3x squared. So that is your final answer. For B, the derivative of ln is 1 over whatever's on the inside of the bracket. That's why we have 1 over the root of 4x plus 2. Then we need to take the derivative of 4x plus 2 to the power of a half. And that's how you would rewrite the root of 4x plus 2. So again, to do this, you take the half to the front, subtract 1 from the exponent, and then you could throw that at the bottom of the denominator to get a positive exponent. Then finally, you would multiply it by the derivative of 4x plus 2, which is 4. For question 2, you need to take the antiderivative of each term. So the antiderivative of x to the power of 4 is adding 1 to the exponent, was how we got our 5, and then you need to divide it by that exponent. That's why I have a 1 over 5 in the front. Then we have 4x, same sort of thing, add 1 to the exponent, becomes 2, and then we would divide that 4 by 2. That's how we got a2 as our coefficient in the front. Then lastly, the antiderivative of 6 is 6x. Then we're going to evaluate it. It would be our antiderivative evaluated at x equals 3 minus our antiderivative evaluated at x equals 2. So in here, this is where I put in my x equals 3, and I start to simplify. And then you do the same thing for 2, so remember to subtract it. Because according to the formula, it's the antiderivative of f of b minus antiderivative of f of a. Then you want to simplify, and your final answer should be 291 over 5. Be careful when you're simplifying. You don't want to make small mistakes when you're adding or subtracting your fractions, so please look over your work on that. For b, we're going to take the antiderivative of 1 over x, and that's going to be ln, absolute value of x. The antiderivative of sine is negative cos, so that's your double negatives will cancel out to get a positive, and then we would have to evaluate it from pi to 2 pi. So we evaluated and plugged in 2 pi first, and then subtracted with the antiderivative, plugging in x equals pi. Then you want to simplify. Because you have ln 2 pi minus ln pi, that subtraction, we can combine our natural logarithm using division. So we have ln 2 pi over pi, which is just ln 2. So your final answer is ln 2 plus 2. For C and D, these are indefinite integrals. We don't have any bounds, so you would just leave it as the antiderivative, but you have to remember to put that plus a constant in the end, because if you take the derivative constant, it just becomes 0. So when you're doing the antiderivative, you have to consider all constants. So the antiderivative of the first one, well, you could rewrite this in terms of exponents, which is what I did first. And I also separated my 2 integrals into 2 parts, into 2 integrals. Then after that, I found the antiderivative. So remember that 3 in the front of the x minus 2 to the power of 3. This is just a number. We can throw it in the front. And then we would add the exponent of 1. So negative 2 over 3 plus 1 is 1 over 3. And then you want to, because this is already a fraction, you're going to multiply by 3. Or it would be 1 over 1/3, which is still 3. Then for our next one, I pulled the 5 out of the front. The antiderivative of 1 over 1 plus x squared is tan inverse x. And then we add the constant. Then for D. The 7 to the power of x, if you took the antiderivative of this would be 7 to the power of x over ln 7. That's what we covered last time. And then we have cosecant squared x. The antiderivative of that is negative cotangent to x. And lastly, the derivative of 2 is 2x. And then we're going to add a constant in the end, because if we took the derivative of constant, it will be 0. And we still get this. So we have to consider that constant. And that would be your final answer. Question 3. We're given f of x and we want to find the critical points. So you need to take the derivative of f and set it to 0, and then factor so you can solve for x. So we got x equals 0 and x equals negative 2, which means these are our critical points because that's when f prime is equal to 0. For b, we want to find relative max and min, and this would occur at our critical points. So we have 0 and 2. I did a number line and did a sign test for f prime. So if you plugged in some number in between negative infinity to negative 2, you're going to get a positive number. Between negative 2 to 0, you're going to get a negative number. And then between 0 to infinity, you'll get a positive number. So that means we're going to be increasing, then decreasing, then increasing. So you're going to have a minimum at x equals 0 because f prime changes from negative to positive there, and then a max at x equals 2 because f prime changes from positive to negative there. For C, find the open intervals where the function is increasing and decreasing and then justify each response. So we're going to look to see when f prime is positive and negative. So it looks like it's increasing between negative infinity to negative 2 and 0 to infinity. And it'll be decreasing between negative 2 and 0. Again, we can use our sign diagram from up here to help us determine that. To find points of inflection, we need to find the double derivative. Now it would be 2x plus 2. We would set it to 0 to find the inflection point. And it seems like it would be at x equals negative 1, but we have to double check. So I did a sign diagram for f double prime. Between negative infinity to negative 1, I picked a number in there, and we get a negative number. And then between negative 1 to infinity, just pick a number in there, say 0, you're going to get a positive number. So because we are changing concavity, we have a point of inflection at x equals negative 1. Then lastly, we need to just state the open intervals where the function is concave up and concave down. So again, you would use the sign diagram to help you determine that. All right, so let's tackle something new now. We covered a piece of the fundamental theorem of calculus, but now we're going to develop another part of the fundamental theorem of calculus. We're going to determine how to take a derivative of a function that is defined as an integral and then see what it means to define a function as an integral. And then once we can do that, we can answer questions about increasing and decreasing concavity and inflection points just like we did before. So let's do example 3. If we want to find the integral from 2 to x, g prime of t dt, we would have to find the antiderivative of g prime of t, which would be g of t. And then we need to evaluate this from 2 to x, which would be g of x minus g of 2. And that's all the information we have, so we just have to leave it like that. For the next one thing at a time, I'm just going to leave this d over dx in the front. And I want to see what this integral is going to look like. But we just calculated that in example 3, so I can exactly write that down. G of x minus g of 2 from example 3. And then we want to take the derivative of this. So this is going to be g prime of x minus, this would just be a number because we're evaluating it, so it's going to be 0 once we take the derivative. So we're just left with g prime of x. With what we just did, we can create a second fundamental theorem of calculus. So if f is continuous on an open interval containing a number, then for every x in the interval, the derivative of our integral from a to x of f of t dt is the same thing as f of x, which makes sense because we're almost canceling this part out. The derivative and taking the integral would just cancel each other out, and then we'll just be writing it in terms of x. So let's do some examples on that. So we have g of x. We want to find g prime of x. Let's simplify this g of x a little bit more by trying to evaluate that. So the antiderivative of f of t is going to be, let's say, capital F of t is our antiderivative, and then we'll evaluate this from -2 to x. This is going to be then f of x minus f of -2. Okay, now let's consider g prime of x. If I want to find g prime of x, I need to take the derivative of this. Okay, so the derivative of f prime of x is going to be little f of x. Because remember, when we took the antiderivative of little f, it became big F. So if we're going to take the derivative of big F, it's going to be little f. Then minus the derivative of any number. Remember, this will just be constant because we're evaluating it. It's going to be 0. So then we're just left with f of x. So if we look at the pattern here, what happened? It looks like we just inserted this x into our f, and that's how we got f of x. And if you look at our theorem here, same thing. This x just went inside here, and then we have f of x. So if we use the same sort of principle for the next one, that means I could just take this x and put it into every time I see a t. So this would be fx cubed minus 4x plus 1, according to the second fundamental theorem of calculus. This one's a little bit more complex because we have functions now, g of x and f of x in our bounds. But first off, I'm going to find the antiderivative of h prime of t, which is h of t. And then we'll evaluate this from g of x to f of x. And don't forget your derivative in the front. So you will take the derivative after. Okay, now we're going to evaluate this. So we have h of f of x minus h of g of x. Then we'll take the derivative, and this is where we're going to use our chain rule. So if at h prime, then leave the inside alone. Then take the derivative of f prime, or take the derivative of f to get f prime. Then we'll take the derivative of h again, leave the inside alone, and then take the derivative of g, which is g prime of x. So what we just found here is going to be the second fundamental theorem of calculus extended. So if f is continuous on an open interval containing a, then for every x in the interval, the derivative of the integral of h of x to g of x of f of t dt is f of g of x times g prime of x minus f of h of x times h prime of x. So this is good whenever you have a function in your bounds instead of a number. So let's do 2 examples. For the first example, I'm just going to evaluate this step by step, and then in example 9, I will use the theorem. Okay, so for example 8, we want to find the derivative of this integral from x squared to 2x of f of t dt, and we have been given these functions as our bounds. The first thing I need to do is find the antiderivative of f. We can just say that's capital F of t and then we'll evaluate this from x squared to 2x. So then we have f of 2x minus f of x squared. Now we want to take the derivative. So the derivative of f is going to be little f. Leave the inside alone, then we'll take the chain rule and take the derivative of 2x, which is 2. The derivative of f is just little f. Leave the inside alone. Multiply it by the derivative of x squared, which is 2x. And that's it. That's our answer. For example 9, we're just going to use this right away. So f of g of x, our f is the root of 1 plus t to the power of 4. But I'm going to insert 4x squared in there. To the power of 4 from the original function. Then we'll multiply it by the derivative of 4x squared, which is 8x. Then minus f of h of x. So again, our f is the root of 1 plus, and then our h of x part is 6x. All this will be to the power of 4. Then we'll multiply by the derivative of 6x, which is 6, and that is our final answer. Now we're going to look closely at what it means to define a function as an integral. So let g of x be the integral of -2 to x of wt dt, and we've been given the graph of that. So this is wtd. So this is w of t. The first question asks us to find g of 0. So g of 0 then is the integral from -2 to 0 of wt dt. So we're finding the area between -2 to 0. Now if you look at these two triangles, they have the same area. When you're below the x-axis, this will be negative. When you're above the x-axis, this will be positive. So when you add the two areas together, you will get 0. The next one, we're going to find g of 2. So g of 2 is equal to -2 to 2 of wt dt. That's from here to here. So you're going to find the area of this, which is 1 times 1 divided by 2. So this is a half. Then you can find it over here as well. This is also a half, but this one is a negative and this one's a positive, so these cancel out. So really we just need to find the area from 0 to 2 within here. So we can section this off to get a triangle and a rectangle. So for our rectangle, we have 2 times 1, so that's 2. And then the area for our triangle, that's 1 times 2 divided by 2, which is 1. So overall area is 3. Lastly, we're going to find g of -3. So this is the integral from -2 to -3 wt dt, which means we're looking for the area of this trapezoid over here. The area of a trapezoid is a half times your base, which is 1, length 1 times length 2. So the first length is just 1, the second one is 2. So that's 3 over 2, which is the same thing as saying a half. Now we need to think about if this area is going to be positive or negative. We initially will think it's negative because it's below the x-axis, but if you look at our bounds, we're going from -2 to -3. Usually we go from lowest to highest, and from our properties we learned last time that this would be equivalent to negative the integral of -3 to -2 of wt dt. Okay, so actually this whole area will be negative times negative 1.5, which is positive 1.5. So this would overall be positive. For the next example, we're going to put it all together. The graph that's given to us is f of t. And we're also been given the function of g of x, which is the integral from negative 1 to x of f of t dt. To complete this table, we're going to plug in all those different x values into our g of x to find what value we're going to get for g of whatever the x value is. So for the first one, we're looking at the integral from negative 1 to negative 3. In other words, we are looking for the area from negative 3 to negative 1. And if we take a look at those two triangles, they are the same, but one of them is going to be positive, the other is going to be negative. So they will cancel out, so you're left with 0. For the next one, negative 1 to negative 2. So that is this triangle right here. That's 2 times 1 divided by 2, which is 1. And it will be positive because our original value will be negative because it's below the x-axis, but our bounds are also backwards. So that negative times that negative is going to give you a positive 1. For the next one, the integral from negative 1 to negative 1, they are the same, and we learned that property. That just means it's going to be 0. Then from negative 1 to 0, we're looking at this triangle, which will have the same value as the other triangle we figured out from negative 1 to negative 2. So that has the same area of 1, but in this case, our bounds are fine, so this will be negative. Go from negative 1 to 1. The first triangle has an area of 1. The second triangle has an area of 0.5. And they're both below the x-axis, so this is negative 1.5. Then we're going from negative 1 to 2. This first triangle has an area of 2 times 1 divided by 2, which is 1. And it's underneath, so that's going to be negative 1. This other one is 2 times 2, which is 4, divided by 2, which is 2, and they will be negative because it's below the x-axis. So overall, our area is 3 here. Then lastly, we have negative 1 to 3. So we already had this one, it was negative 3. We just need to add this trapezoid in, which is half times 1, and then 2 plus 3. 5 divided by 2, which is 2.5, and again it's below, so we do need that negative in there. So altogether, it's going to be negative 3 plus negative 2.5, which is negative 5.5. For B, we want to find which intervals g is increasing or decreasing. To determine that, we're going to look at the values of our f of t graph. So we're going to have an increasing function for g whenever f of t is positive, and it'll be decreasing whenever f of t is negative. So for increasing, this occurs here, and that's it. So from negative 3 to negative 2, and that's because f of t is positive. And then for decreasing, we're going to look at all values that are negative. So that's from negative 2 to 0, and then from 0 to 3. And that's because f of t is negative here. For C, we're going to look at intervals on which G is concave up or down. In this case, we're going to evaluate when f of t is increasing or decreasing. For increasing and decreasing. So if we have concave down when f of t is decreasing and concave up when f of t is increasing. So f of t is decreasing between -3 to -1 because our slope is negative there. So we have this section, and then we have it again from 0 to 3. Then we'll have concave up, only in that one section from -1 to 0. To look for values of G, to find the max and min, we're going to see when f of t changes from positive to negative. So that occurs at only one place, at x equals -2. And that would be our max, because we're going from positive to negative. So we have inflection points at x equals -1 and at x equals 0 because we're going from decreasing to increasing and then increasing to decreasing. So the first inflection point's at x equals -1. That's because f of t changes from decreasing to increasing. And x equals 0 is the other inflection point because f of t changes from increasing to decreasing. Then the last thing we're going to do is graph g of x. We already found a table of values in A, so that's exactly what we're going to graph. So we point at -3, 0, at -2, 1, at -1, 0, 0, -1, 2, -3, and 3, -5.5. And then we can connect these. So that's kind of what g of x looks like.